Hi, I'm Khadija, and welcome back to this machine learning fundamentals tutorial. Today we'll be talking about supervised learning. You will learn what it is, how it works, various algorithms to choose from, and different applications. So if you recall from our previous example, where we had a teacher teaching students, so teaching with examples and their corresponding answers. Like in this case, the teacher will show them various pictures of apple with their corresponding label, which is apple, various pictures of a banana with the corresponding label, banana. So when the teacher shows a new picture of an apple that the student has not seen before, the student should be able to say, this is an apple. So that's what supervised learning is. You're given examples with their corresponding outputs, answers, and when it's trying to test on a new data it has not seen before, it should be able to say the correct label for it. So it's just a type of machine learning that involves training a model with a labeled data set. So each input data point in the training set is paired with the correct output, also known as a label, and that serves as an answer key. So it learns to predict the output from the input data by finding patterns in the training data set. So let's understand data in supervised learning. You have different features and labels. So in our fruit case, the different features will be colors, size of a fruit, while the labels are the correct answers, for example, apple and banana. So the goal is for our model to learn to predict labels based on features. So now, here we have an example of how data might come in the traditional supervised learning. We have red, color red, size small, fruits apple as the label. So if it's red and it's small, say it's an apple. If it's yellow and medium, banana, green and small, apple, and so on. So let's say it trained with this one here. If you then give it red and large, can it correctly say it's an apple? So that's supervised learning. You give it different data explaining the features and the size and the corresponding label, fruits. And when it sees a new color and size, can it give the correct fruit label, either apple or banana? So let's know our task. There are two types of supervised learning task. It can solve two main problems. We have classification, like deciding if a photo shows a cat or a dog, discrete set of labels. And we have regression, like predicting the price of a house based on its size and location, continuous outputs. So you need to decide if your task is more like sorting things into groups, classification, it goes either here, here, or here. Cats, dogs, fish, elephants, anything. But it should go in a specific group. Or you can decide if it's like guessing a number, regression, continuous outputs. So let's look at common algorithms in supervised learning. The first one we'll look at is linear regression. And as you can see from the graph, it's like trying to fit a line through a set of points. So each particular one feature could have its corresponding output. So let's say you're trying to predict a house based on size. You can see here the size is on the horizontal axis, the price is on the y-axis. As the size of a house is increasing, the price is increasing, if you can see from the diagram. And we can have a straight line that can fit through that set of points. So when you have a new size, it can give you a correct price. So it's one of the most widely used algorithm regression tasks, where the goal is to predict a continuous output. So you need to be able to fit a straight line through the data points. For example, if you're trying to predict a student's score based on their study hours, that is linear regression. By linear, it just basically means it has a straight line to its predicted output. For example, let's say for every hour you work, your salary doubles. So that is linear regression. Let's look at logistic regression. So that's why its name, logistic regression, is used for classification tasks. It estimates probability using a logistic functions, and that outputs values between 0 and 1. So let's say you're trying to decide whether to bring an umbrella. If the chance of rain, like a probability score, is high enough, you decide to bring it. If not, you leave it at home. So logistic regression calculates the probability of an event, for example, rain, and makes a decision based on whether the probability is above or below a certain threshold. So it's like deciding at 50% chance of rain. If there's 60% chance of rain, you bring an umbrella. If there's 30% chance of rain, you will leave your umbrella at home. You can use this to determine whether an email is spam or not spam based on its content, sender, and other characteristics. Now, let's look at decision trees. So they're a nonlinear model. They're used for both classification and regression. And they split data into branches to form a tree structure based on decision points over the input features. So each decision point in the tree represents a choice between two or more paths, leading to different outcomes. So let's say you have like a game of 20 questions, and you're trying to narrow down an animal your friend is thinking about. And you do this by asking yes or no questions. So each question splits the possibilities until you correctly identify the animal. For example, what is the shape of the animal? Yeah, is it big? Is it small? What's the size of the animal? Is it big? Yes or no? Then go to this branch tree. Does the animal stay? Can the animal stay in a home? Yes or no? Go to this particular decision. And so on till it gets to the answer. Then we have random forests, which build upon the concept of decision trees. So instead of creating one tree, it constructs many trees with random subsets of features and then averages their prediction. So it can build on the 20 questions game, like the previous one, by having a whole forest of different 20 questions games played simultaneously. Each game or decision tree has slightly different rules or questions, but they will all try to guess the same thing. In the end, the most common answer among all of the trees is chosen. So it's like getting a consensus from a crowd of experts. So that is random forest. So it just builds upon the concept, and then instead of having one tree, it has many trees. So let's look at support vector machines. They are powerful for classification tasks. They work by finding the best boundary that separates classes of data. The boundary is chosen to be the one where the distance between the nearest data points of each class is maximized. So let's say you're at like a party and you need to divide the room into two groups to play a game. So an FVM finds the best possible line that divides the two groups so that they are far apart as possible. So now you can ensure clarity and reduce confusion over which side someone should be on. So this is what it is. So can you see this line that's dividing the two groups? You want to make sure they are as far apart as possible. If you tweak this line, they may not be as far apart as possible. So you need to make sure this line is one where both groups are as far apart as possible. That is support vector machines. So now let's look at k nearest neighbor. So it's a simple intuitive algorithm that classifies a new data point based on major categories of its k nearest neighbor in the feature space. So k is the amount of neighbors you want to look at. If you're looking at 2 neighbors, k will be 2, 3 neighbors, k will be 3. So it's like looking around your neighborhood and seeing how others are decorating their front yards and then deciding how to decorate yours based on the most common styles you see. So this is how KNN works similarly. So you can also use this when you're trying to recommend movies. So if you've rated highly, and if you've rated movies highly and find that others who like similar movies, You can then recommend movies that those similar users have also rated highly. So the app uses the nearest neighbors, so that's users with similar tastes, to predict your preference. So that's key nearest neighbors. So the amount of neighbors, you look at what they're doing, and then you can use it for a new person based on similar tastes, for example. So naive-Bayes classifiers are a family of simple probabilistic classifiers based on applying Bayes' theorem, which is here, with strong naive independence and assumptions between features. So naive Bayes is simply based on assumptions. So you're making a prediction based on assumptions. So if you know that someone likes romantic movies and most romantic movies are dramas, you might guess they like a new drama. So it uses probabilities and these kinds of assumptions to make predictions. So you can also use this in spam detection. So it looks at what's in spam detection that are commonly found in spam emails. For example, you have win, you have free. So if a new email contains a high proportion of these common words like win and free, it will be classified as spam. So that's naive based on assumptions. Then we have gradient boosting machines, GBM. So they are a group of machine learning algorithms that combine multiple weak learning models together, and you create a strong predictive model. So imagine a group project where each presentation, the team focuses on improving the weakest part of the project. So that's how GBM works. It builds one model and then improves it step by step by focusing on the mistakes the previous model made. So now let's look at AdaBoost. So AdaBoost is a boosting algorithm that can be used in conjunction with many other types of learning algorithms to improve performance. The output of other learning algorithms, weak learners, is combined into a weighted sum that represents the final output of the boosted classifier. So just think of it as a team of learners, where each new team member focuses more on the questions that the previous members got wrong. So that is adaptive boosting. So this way, each learner tries to correct the mistakes of the one before, making the team's final decision stronger. So you can be used in a facial recognition system that needs to identify faces in various lighting conditions. Adaptive boosting can help by combining multiple weak classifiers. So you can have different systems that focus on a specific lighting condition, and then they can be combined to create a stronger one. So let's look at extreme gradient boosting. So it's an implementation of gradient boosted decision trees designed for speed and performance. It's highly flexible and versatile algorithm that supports regression. So it's just a more efficient, faster version of GBM. So if you have a team of experts who not only learn from previous mistakes, but also do it quickly and effectively. So it's like a favorite choice when performance and speed are priorities. We have another one, lasso regression, least absolute shrinkage and selection operator. So the type of linear regression that uses shrinkage. Shrinkage is when data values are shrunk towards the central, like the mean. So think of lasso regression as a way of simplifying a very busy and complicated decision by ignoring the less important details. For example, if you're going on vacation, you might only want to take the important things and leave behind the things that are not important. Similarly, if you're decluttering a room, you might say, okay, leave the important things out and remove all the things that are not important. So this is lasso regression. Then we also have ridge regression. So it's like balancing your team skills in a relay race to get the best overall team performance. So it's a technique for analyzing multiple regression data that suffer from multicollinearity. So by adding a degree of bias to the regression estimates and reduces the standard errors. So let's say like it's in real estate. So features such as square footage, number of bedrooms, and number of bathrooms may be highly correlated. That is multicollinearity. So you can make a guess that as the size of a house is increasing, the number of bathroom is also increasing. So they have collinearity. So that is ridge regression. So now let's move on to what to consider when choosing an algorithm. You can look at ease of understanding, the speed and accuracy, and the size of data. So when we need to sort data into categories, you have decision trees, logistic regression, SVM. You can also look at data size and quality. So for large data sets, random forest or XGBoost. If you have missing values or noise, you have random forest and AdaBoost decision trees. They can handle this. If you're looking at accuracy and which one you want to accuracy versus interpretability. So if you want to be able to interpret, so maybe decisions will need to be explained when the machine makes a choice. So you can use simpler models like naive Bayes or logistic regression because they're very interpretable. They can explain something to the user. Then we have high accuracy. So remember, XG boost is one. So word model complexity is less of a concern as well. So predicting numbers. So when it comes to regression, linear regression is good. So linearity of data. So remember, you can fit data into a straight line, so you know the relationships between variables is easier. So for example, if you're walking and as each time you walk, size of a house is increasing, or let me say you're trying to cook food for one person, if they need 2 cups, if it's 2 cups for one person, when it's 2 cups, double it and so on. Also feature importance. When it's crucial to understand the impact of different features, models that provide clear insights into feature importance like lasso regression are important. You can also have prediction versus model simplicity. For example, GBM and XGBoost high prediction accuracy, lasso and ridge regression simpler but effective methods for data sets where interpretation and also avoiding overfitting are more critical. You'll learn what overfitting is soon. Also, handling of outliers. So, outliers are simply data that don't correspond to most of the values. So, let's say you have 2, 2, 2, 2, 3, 3, 3, 3, 4, 4, 4, 4. If you see another data that's like 25, that's an outlier. It's very far from one. So, random forest and XGBoost can handle outliers, but linear regression cannot. So machine learning is data driven. So first you need to collect data of images and their labels or classes. Then you should use machine learning to train this to get a classifier. Then you test this classifier on a different set of data, excluding the ones used for training. So let's say you have 1,000 images of cats and you're saying this is a cat, thousands of dogs saying this is a dog, thousands of mugs saying this is a mug, and thousands of hats saying this is a hat. You first give the system 70% of your data and say this is a cat. And you leave out 30%, let me say 3,000 since we're using 10,000. If you're using 10,000, you give it like 70,000 images. Sorry, if you have 10,000, you give it like 7,000 images and you say this is a cat and you show it the pictures of a cat. Will you leave out the remaining 30%? And then you can test this without giving it the labels. So you show the system the image of a cat. If it says it's a cat, then it's good. So that's what the split is for. So you can have 70-30 split, 70% for training, 30% for testing. You can have 70%, 90% for training, 10% for testing, and so on. So the process starts by feeding the model a large amount of labeled data. The model makes prediction based on this data, and each time it makes a mistake, it adjusts itself to improve. Over time, it gets better at making accurate predictions. So you also learn in another video how to evaluate a model. So you need to check how well our model performs using new unseen data. And we can use metrics like accuracy to measure how often the model's predictions match the true answers. So it's like seeing how many answers the student got well on a test. We have something like overfitting and underfitting. So learning too much or too little can both be problems. So overfitting is like memorizing a book word for word but failing to understand the story. Underfitting is like understanding too little to retell the story. So you need to strive for a balance where the model learns the patterns well but can also adapt to new unseen data. So with underfitting, it's not really learning on the training data sets. So when it comes to testing, it's still doing poorly. With overfitting, it learns too much to that training data set that when it comes to new data you want to test, it is not doing well. And there are different applications where supervised learning can be used. For example, in spam detection, in diagnosing a disease, it can also show like a picture of a tumor and you can see whether this is benign or malignant. So thank you for watching. By understanding and applying the supervised learning process effectively, we can build models that not only perform well on known data, but can also adapt and respond correctly to new unseen information. So in the next video, we're going to speak about another type of machine learning. And when we finish with the types, then we're going to go to the practical session. So thank you for watching.